Everybody, we're going to talk about Chapter 5 in this video, and specifically we're going to talk about Chapter 33, Ionic Compounds. Now, we've probably touched a little bit on this in either in class or in previous videos, but one of the things that we need to know going in here is that we can determine the charge on an ion by using the periodic table. And so I have my periodic table here, and basically we can tell that anything in this column is going to be a 1 plus, and then a 2 plus, and remember those are going to be attracted to the negative ions, which are found on this side. The noble gases, they all are 0, and then we have 1 minus, 2 minus, 3 minus, okay? And those are going to be the compounds that we deal with most of the time. Now, coming back here, the important point that we're trying to make here is that compounds have to be neutral. When you take the charges on the ions and add them up, they have to be neutral. So when we take something like a calcium ion, which we know has a 2 plus charge because of the periodic table, and then we have an oxygen ion, what we know is that those two things are the same. They cancel each other out. So when we make the formula, it's going to be CaO. Now, that's a little bit different because we can now take a look. What if we don't have the same charge? What if we have lithium, which is a 1 plus ion, and then we have something like nitrogen, which is a 3 minus? Well, the point is that these things have to cancel each other out. And so that's what I'm saying, is that we combine various amounts of each of these ions to make the compound neutral. So if we have 1 plus and 3 minus, what do we need more of? We need more of the 1 plus. So I'm going to add another 1 plus, and I'm going to add another 1 plus. So I can only add the elements that we have available to us when we're making the compound. I'm not going to just pick other random compounds out of the air. So now we have 1, 2, 3. We have a total of 3 plus. And how many lithiums did we need in order to do that? Right, we needed 3. So it's going to be Li3. The number in the subscript tells us how many of them we needed, and then N. We only have 1 N. And then we can do the same thing. We can continue to do that with other ions. What if I take strontium, which is a 2 plus, and then take something like phosphorus, which is a 3 minus. Okay, this is the most difficult of them, is because here so we need more pluses. So by adding another strontium, that doesn't get us evened out. We have a 4 plus here, and we only have 3 minus here, so we're going to have to do another phosphorus. And so now we're at 6 minus, and there's 2, 4, and now another strontium for 2 plus. Okay, so that's 2, 4, 6, that's 6 plus, there's 2, there's 3, there's 6, there's 6 minus, and so how many strontiums do we have? SR2, SR3, P2. Okay, and so that's kind of how this works, is you balance out the charges by kind of adding up amounts of the elements that you need, the ions that you need. Now, ions don't have to be single ions. There's a whole category of ions that are called polyatomic ions. Okay, up until this point, we've only dealt with monatomic ions. Polyatomic ions are ions, but it's a group of atoms that have a charge as one big unit. So NO3 has a 1 minus charge, and that's this whole thing within that parenthesis there. So that whole charge is 1 minus. Okay, so if I couple that with calcium 2 plus, I have a 2 plus and a 1 minus. I need it to be neutral, That's what we're trying to do. Let's make it neutral, so that means I need another NO3 with a 1 minus. So now the total amount of minus is 2 minus, and I have 2 plus. So the formula here is CaNO3, and then I'm going to put this in parentheses because it's a polyatomic ion, 2. Okay, so it's treated a lot, this polyatomic ion is treated a lot like just a regular old ion, except it has many atoms together. Let's do another one. Okay, let's, what if I have lithium, and then I have this polyatomic ion, the PO4 3 minus. Okay, you're not going to have to memorize this name, nor are you going to have to memorize the charge. Okay, but we can determine the charge on lithium. The lithium ion is 1 plus. We look at the periodic table, figure that out, and now we have a 3 minus. So that means we need another 1 plus. So that's up to 2 plus, and we need another 1 plus. That's up to 3 plus. And this is at 3 minus. So this is 3 plus. This is 3 minus. They're equal and opposite to each other. They cancel each other out. So we're going to do Li3PO4. Now we don't have to put parentheses around it because there's only one of them. Okay. Let's try one more here. Okay, so another polyatomic ion. Let's do barium. Okay, barium is a 2 plus. Okay, and then let's do this OH 1 minus, or minus 1. So we have a 2 plus and a 1 minus. So that means we need another one of these. We want to get the same number. So this is 2 plus, this was only 1 minus, so we're going to add another 1 minus. So that means that this is 2 plus. By adding another one of these, that's 2 minus. They cancel each other out. And so now this is BaOH. And now that we have more than one of them, we're going to put this in parentheses and put 2 there. Okay, that means we have 2 of everything in the parentheses. Should we try one more? I think the thing to do is I'll give you the elements and then you pause it and see if you can get the right formula for the thing. Okay, so what if I have rubidium with a 1 plus charge, and then I have PO3 3 minus. Okay, so pause it and see if you can do it. Okay, so now here's the thing. This is a 3 minus, this is a 1 plus. So we need RB with a 1 plus. We need another RB with a 1 plus. We're not going to change the formula. We're not going to change the symbol, nor are we going to change charge. That's already stuck. So now we have a 3 plus. Here we have a 3 minus. Notice they cancel each other out. And so that means we have RB3 PO3. We only needed 1 PO3, so we're not going to put that ion in parentheses. Okay. And so it's funny that all of these ions that I'm showing you, all of these guys dissolve in water. And so when these compounds dissolve in water, we call that that compound has a solubility. There's all sorts of solubility rules where compounds will dissolve in water. Some will dissolve very quickly. Excuse me. Some will dissolve slowly. Some won't dissolve at all. Some will only dissolve a little bit. But for the purposes of this class, we're just going to stick here and we're going to say if it's soluble, it's soluble. If it's not, it's not. We're not going to have varying degrees of solubility. The other thing that happens, if it's soluble, if something dissolves in water, if it's an ionic compound and it dissolves in water, it conducts electricity, which is a really neat property of ionic compounds. Ionic compounds can conduct electricity when they're dissolved in water. Covalent compounds can't. Okay, and so something like salt water. Salt is NaCl. It's an ionic compound. It's a metal and a nonmetal. That conducts electricity when it's dissolved in water. Sugar water. Sugar is a covalent compound, C6H12O6. It's all nonmetals shoved together. So when sugar water is applied a current, it does not dissolve. It does not conduct electricity. So it's kind of neat. Ionic compounds, you can tell if they're ionic because they will conduct electricity when they're dissolved in water. Water does a lot of neat stuff, and so that's kind of neat. So that's ionic compounds and how ionic compounds can be used and be written using their charges with both monatomic and polyatomic ions. Have a great day.